All right, so here we go with this. So yesterday we introduced and we said, okay, a buffer. A buffer has to have a weak acid and its conjugate base, or if we use a base like we're going to use here, it's going to be a weak base and its conjugate acid. Okay, if we have that available, we are going to use that Henderson-Hasselbalch equation. Okay, so Henderson-Hasselbalch equation says, I'm going to write it next to the example here, pH is equal to pKa plus the log of our base on top over our acid. Okay. Now, again, like we talked about yesterday, I do not need to put molarity or concentration. I can put moles of base over moles of acid. Okay. Simply, this is a ratio. All right. Now, what we have here is this. We want to utilize this formula so that we know how many moles of ammonium chloride that we must add to 2 liters of a specific solution here that already contains 0.1 molar NH3. Okay, and now I gave the equilibrium expression down below, or at least the equation. We are given this time our pH. All right, so I'm going to start out and I want to ask you, what is our initial concentration or value of a substance here? 0.1. Yes, perfect, 0.1. I was hoping you'd get that, and you did. 0.1 molar NH3. So we know for sure, typically you would say, hey, that's our initial concentration. But with the Henderson-Hasselbalch equation, we can just say, hey, 0.1 molar, that's what we're going to use because this is going to play a factor in our formula. Now, just FYI, NH3 is a base. Notice how it accepts an H+. It is a base, okay? So we're going to have to do some thinking about this. But with NH3 is this. We first need to find some more info, and that info is this. Our pKa. Does anyone remember from the previous day of notes what pKa is actually equal to?
Negative log of Ka.
Yes, negative log of Ka. Okay, so pKa, I'm going to write this just below here. pKa is equal to negative log of Ka. Well, that's great. If we try to find the Ka of NH3 on our sheet of paper with our equilibrium constants, we're not going to find it. But we are going to find for NH3, because it's a weak base, we're going to find not Ka, but Kb. And if we find this on the chart here, Kb is given at 1.8 times 10 to the negative fifth. Now, again, I can't use this because this is not Ka, it is Kb. So what, does anybody remember, how could I convert my Kb that's written down right now to Ka?
Subtract from 1.8 times 10 to the negative 4.
Okay, you're on track here, but we'd have to do just a little bit more than that. We got to use that Kw formula, which equals Ka times Kb. Okay, so just a little bit more work here. Kw is always a constant. We learned that from the last unit at 1 times 10 to the negative 14th equals our Ka, which we don't know, times that Kb that we just looked up, which was 1.8 times 10 to the negative fifth. Now, how do I get this all by itself, or how do I get Ka all by itself? Divide by that 1.8 times 10 to the negative fifth. All right. So I'm going to go ahead and I'm going to do that in my calculator, and we're going to see what we get for our Ka. So I'm going to take 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. And when I do that, I'm going to round here, significant digits here. My KA is going to be 5.6 times 10 to the negative 10th. Okay. 5.6 times 10 negative 10th. All right. Again, we still need to find our pKa. So we're going to plug this back into our value here at the top, or back into our formula. And so when we do that, our pKa of interest is equal to the negative log of 5.6 times 10 to the negative 10th. And our pKa, if we do that, negative log 5.6 times 10 to the negative 10th is going to equal 9.25. Okay. So now we can start plugging in and playing into our Henderson-Hasselbalch equation, the equation that we wrote down right here at the top. We are given our pH in the problem. It says, hey, this gives us a pH of 9.00. So right away we can start saying, okay, 9.00 is equal to our pKa, which we took all that time just now to find, which is 9.25 plus the log, of our base on top. Do we know our base?
0.1.
Yep, very good. And I'm just going to write this down just so we remember this is our base. Okay, it is 0.10, and we could put molar. Okay, all divided by, now do we know our acid? No. So I'm going to put this in brackets because we are using concentration. This is the concentration of our acid. Now, we just solved this, and we just got to be careful via algebra. Okay, so we got to get this 9.25 by itself. So we're actually going to, because it's attached via addition, we're going to subtract 9.25 on each side. Now, 9 minus 9.25 would give us what number?
Negative 0.25.
Yes, negative 0.25 is now equal to our log of 0.1 molar, all divided by that concentration of our acid. Now, I do want to walk through this because right now, at this point in time, we have to get rid of this log. So we take the anti-log, or the inverse of the logarithm, which is simply 10 root. So by taking 10 root log, we get rid of this. What we do to that right-hand side, we got to do the left. And so in our calculators, we're going to put 10 root, or you could hit second log, negative 0.25. And when we do this, we end up, I'm going to write 3 decimals down, 0.562 equals, now that we've gotten rid of our log there, simply equals our 0.1 molar over the concentration of the acid. And so all we would have to do at this point in time is this. We would cross multiply, and so we would end up with this. When we cross multiply 0.562, you could say really that's an X. We would end up with 0.562 times the concentration of our acid equals that 0.1 molar. And so how do I get the concentration of the acid all by itself? Divide by that 0.562. All right, so I'm going to divide each side by 0.562. Divide by 0.562. And so when I take 0.1 divided by that 0.562 answer, I just typed in the other answer, I get, by the time I round, our concentration here of our acid, concentration of the acid is going to be 0.18 big M. Now, we got to think about this because of this, and I kind of skipped right over it when I started, but we have 2 liters of a solution, and we want to find how many moles of NH4Cl that we need. So we got to do one more extension off of our concentration of our acid. We got to take this 0.10 or 0.18 molar, and we got to set it equal to some number of moles, and technically that number of moles is going to be NH4Cl because of the common ion effect, all divided by the total solution, which is 2 liters. So how did we get X, our number of moles here? Yep. So we take 0.18 times 2.0, and we get 0.36 moles of NH4Cl that is needed. Okay. So the point is this: we can use the Henderson-Hasselbalch equation to produce a solution with our desired pH. All we have to do is insert our certain quantities. Now, I want to point this out here. Notice here, our desired pH 9 is lower than the pKa 9.25. If it's lower, it means it's more acidic. And so think to ourselves, our acid concentration is 0.18 compared to our base concentration is 0.10. Is that more acid or more base in our solution here?
More acid.
More acid. So it should make sense that the pH gets lower than the pKa. Okay, it's kind of just a self-check here through that. Questions? Does anybody need this? All right, so that was one of our big problems for today. The other one, we just have to do some thinking about this. All right, with a buffer, there's a couple things with a buffer. I'm going to actually start down with this point number 2. Buffers have a specific range, and that specific range is within plus or minus 1 pH range of the pKa value. Okay, so for example, our last problem there with ammonia had a pKa of 9.25, and so the ideal pH range of a buffer that uses ammonia and ammonium, the item we just saw there, would be between 8.25 and 10.25, right? Plus or minus 1 off of the pKa. Any more or less than that, or I guess more than that, is going to start to affect the pH a lot more and kind of not make the buffer as effective. Now, the top point here is this: buffer capacity. 2 things really drive it. The more even we can get the concentration of our acid and the concentration of the conjugate base, the more even they are, the closer they are together, the better the buffer is, because some of that acid is absorbed by the conjugate base, some of the base is absorbed by that acid, vice versa. Also, more concentration we have, the bigger or the more effective the buffer is. So if we have 0.1 molar acid and base, it's less powerful, you could think of it like that, than our a concentration of something like 6 molar. All right, So the more stuff we have in, the more effective the buffer is. All right. Any questions on this? Anybody need it? Okay. All right. So now we get into this. And I write this down, but it's almost easier to see an example here. The point of a buffer is it's supposed to not be affected very much by adding an acid or base, specifically a strong acid or a strong base. Okay, so if we have a buffer, remember we have to have a weak acid and its conjugate base. If we have that and we add some acid, it shouldn't really affect the pH a whole lot. It will affect it a little bit, but not a whole lot. How that affects it, it says it uses stoichiometry. Okay, the one thing I really don't like about how I formatted this is that if we add a strong acid to a buffer, not only is it going to affect the base concentration, but it also will affect the acid. So bottom line with this, and I don't have it written down, is that if we add a strong acid or strong base, it will affect both the acid and base that we have in our buffer. All right, so we have to think about this in twofold. Sometimes I even forget, all right, I added a strong acid. I have to make sure to add and subtract appropriate ways, just like we saw with our change. Okay, questions? All right, does anybody need this? Okay. All right, so here we go with this. A buffer made by adding 0.3 mole of acetic acid, that's acetic acid, to 0.3 moles of sodium acetate. They make exactly 1 liter, which is really nice. I'm going to actually use moles here, of a solution, and the pH of this buffer right now is 4.74, okay? We want to know what is the pH of this solution after 5 milliliters of 4 molar sodium hydroxide is added to this solution. Okay, so the first thing that I want to think about here is this. What do we have? All right, so acetic acid here, acetic acid is this quantity right here. So acetic acid, right now we have 0.300 moles of our acid. So I'm just going to write that down. 0.300 moles of this acid. And we can use moles. Remember, the Henderson-Hausbach equation is really nice. It's a ratio. That ratio is not going to change as long as they're dissolved in the same volume of water. So we got 0.3 moles. And then of our sodium acetate here, of our sodium acetate, we also have 0.3 moles of our conjugate base. All right. Now, what we need to think about is what is happening to our concentration as we add sodium hydroxide. And first off, is sodium hydroxide a strong acid or a strong base? Has OH.
Strong base.
Yes, strong base. All right, strong base. Keep that in the back of your mind as we go through this. Okay. Now, what we have to think about is we've added 5 milliliters of this 4 molar solution. So down here in about halfway down, I'm going to say this. I'm going to do some math here. 4 molar is going to be equal to some number of moles of I'll call it just a base here, specifically strong base here. All divided by, it's not milliliters, but in our molarity formula, it's what? Liters. So technically 5 has to get divided by 1,000 to get us 0.005 liters, right? Just the definition of molarity. We cross multiply. So I take 0.005 times 4, and this gives us 0.02 moles of strong base added. Okay, now I'm going to lower this down just a little bit here with this information I wrote down in orange, because we are going to need a little space here to talk about this. Maybe. Yes. So what this means is we've added a strong base. Now think to yourself, a strong base, is it most likely going to react with that strong acid or is it going to react with the acid or the base? It is going to react with the acid, and there's a little bit more to that. But what happens? It reacts with the acid, so the base reacts with the acid, and it takes away exactly 0.020 moles of our base. So if we take 0.3 minus 0.02, we end up with 0.28 moles of acid that remains. Now, this is the part that I always have to think about here on these types of problems is this. Just like we had in our change category for our ice charts, we subtract some out of the acid, well, we're still adding a base. So on the other side here, we need to add 0.020 moles of base to our base side. Okay, so when we do this, we would end up with 0.320 moles of our base. Now, to calculate our formula, all we need to do is this. We just need to plug this information back into the Henderson-Hasselbalch equation, which our pH is equal to our pKa plus our log of base over acid. And are you guys okay if I just give you the pKa of acetic acid? Okay, pKa of our acetic acid, if I take the negative log of its Ka, I get a value of 4.74. Okay, so I'm just going to write that down. The pKa is equal to 4.74. And we have this, all right? We want to find the pH. So we say pH is equal to our pKa, which I just told you is 4.74, plus the log of our base, which after we added an AOH is now 0.320, and it's okay to use moles, all divided by our acid, which after we did our subtraction here is 0.280 moles of our acid. So here we go, finding our new pH here with this. If we take 4.74 plus the log of 0.32 divided by 0.28, we press enter. This actually rounds to exactly 4.80. Okay. Now, just think about this. 4.80 is not that much different than 4.74. We also added a strong base. So does it make sense that our pH got bigger? Yeah. So you can always kind of do a double check in your head there with how the pH differs. Okay. Next part, we're not going to go in crazy detail because it's not much different. But does anybody need this here? Okay. One thing, I'm going to copy down this information right here and paste it here in just a second. But now, on the bottom of your sheet here, we now have the same exact scenario, but now we're adding a strong acid, okay? So just for your information here, remember, we started out with 0.300 moles of our weak acid, and on our other side here, we had 0.300 moles of our weak base, okay? Then think about this, and this is where I'm going to copy the info from my previous slide. We're adding not a strong base anymore, but we're adding a strong acid, okay? So think about this. If we add, and it's the same concentration and same volume, if we add 0.0025 or 0.002 moles of our strong, again, not base, but acid, now think about what happens. And you guys told me we had a strong base, it reacts with the acid. This time we have a strong acid, it reacts with that base. And so this time here, we actually need to subtract that 0.020 moles from our base. And so when we do that, the base that remains would be 0.28 moles of base, okay? And then this time, because we're adding acid, we need to add our 0.02 moles on our right-hand side, and we would end up with 0.320 moles. And all we need to do is this. We need to use the same Henderson-Hausbach equation, and we'd say, all right, pH equals that pKa, which I gave you before was 4.74, plus the log of our particular base. Now it's 0.28 moles over our acid, which is 0.32. Okay, so we plug this in our calculators real quick to end this. 4.74 plus the log of our base, 0.28, divided by our acid. And we get a pH. Now our pH is 4.68. Okay. Now, again, we added acid. So does it make sense that the pH got lower? Okay, kind of our double check. Buffers, the pH is not going to change much. Okay. Any questions on any of this info here?
Was the PKA being 4.74? Does that have anything to do with the pH of the buffer being 4.74?
Yes, I'm glad you brought that up. So Hannah had a great question. pH, I told you on the front end of this problem, the pH was 4.74. Why it's 4.74 is because we have equal number of moles of weak acid and equal moles of its conjugate base. If they're equal, then the pH will equal the pKa. And that's a really good point that you brought up and realized. Good question. Anything else?